Hello everyone, welcome to Electrical Paathshala 2. In today's video, we are going to study about standard test signals that we use in control system subject for the analysis of a control system. Now these standard test signals are used as input to the system. So we have four standard test signals, which are impulse signal, step signal, ramp signal and parabolic signal. So we will talk about them one by one. So first of all, we will talk about impulse signal. So impulse signal is also known as sudden shock. So guys, impulse signal is a very important signal in control system subject because the stability of a system, stability of a control system is defined with respect to impulse signal only. For that you have to recall the definition of stability, which says that stability is the ability of a system to recover from sudden shock. So what is sudden shock here? Sudden shock means impulse signal. That's why stability of a system is defined with respect to impulse signal only. Therefore, impulse signal is a very important signal in control system subject. So impulse is shown by short duration pulse. So you can see here in this diagram that this is an impulse signal, and here epsilon tends to 0. So this signal is a short duration pulse, and this represents our impulse signal. So impulse signal is defined by delta t is equals to limit epsilon tends to 0 RT. Now in this diagram you can see that if we put epsilon is equals to 0 in these two terms, then these two terms will become 0. It means that width of the signal will become 0. And if we put epsilon is equals to 0 in this term, then this term will become infinite. It means that if epsilon tends to 0, the width of the impulse signal tends to 0, and height of the impulse signal tends to infinite. Therefore this impulse signal can also be shown like this. Here you can see that this is an impulse signal at a particular time instant t is equals to 0, and here the magnitude of the signal is infinite. Therefore we can write that delta t is equals to infinite when t is equals to 0, and 0 when t is not equals to 0. You can see that in the diagram also. At t is equals to 0, the magnitude of the impulse signal is infinite, and when t is not equals to 0, whether it is t is less than 0 or t is greater than 0, the magnitude of the impulse is 0. That's why we say that impulse is also simulated as sudden shock, because you can see here that at t is less than 0, the magnitude of the input signal or impulse signal is 0, but at t is equals to 0, suddenly the magnitude of the signal becomes infinite, and soon after t is equals to 0, again the magnitude becomes 0. That's why we say that impulse signal is also known as sudden shock. Now here we will see what is the area of impulse. Area of impulse is given by integration of delta t with respect to dt from minus infinite to infinite. That is, area of impulse is given by time integral of impulse signal with respect to time from minus infinite to infinite. Now the area of this short duration pulse can be given by width into height. So epsilon into 1 by epsilon, and that will give us, these two will cancel out, and that will give us 1. So area of impulse is always 1, and this is also known as weight of impulse. But guys, in control system subject, we cannot take magnitude of impulse signal to be infinite. Why? The answer lies in the definition of stability. So definition of stability says that stability is the ability of a system to recover from sudden shock. Suppose a system is subjected to a sudden shock, then it will deviate from its initial working state. But if the system recovers from that shock and regain its initial working state, then we say that the system is stable, and this special ability of the system to recover from a sudden shock is known as stability of the system. Now stability is defined under bounded input, bounded output criteria. Bounded input, bounded output criteria. Stability is defined under this criteria, which means that for a bounded input, the output of the system should be bounded. Now here sudden shock is the simulation of impulse signal. So as the input is bounded, it means that magnitude of the input is finite. Therefore we cannot take magnitude of the impulse signal to be infinite. That's why in control system subject, the impulse signal is given by delta t is equals to 1 when t is equals to 0 and 0 when t is not equals to 0. Here this 1 is the area of impulse or weight of impulse. So the graphical representation of this impulse signal is this, that at t is equals to 0 there is an impulse signal at t is equals to 0, and magnitude of that signal is 1, and this 1 represents area of impulse signal. So this is impulse signal in time domain. But how to represent impulse signal in frequency domain or S domain? For that we have to take Laplace of impulse signal. So in frequency domain or S domain, or we can say that Laplace of impulse is 1. You should remember that this result. So Laplace of impulse signal is 1. So this was about impulse signal. Now our second test signal is step signal, which is also known as sudden change. So step signal is given by ut. Ut is equals to a when t is greater than or equals to 0, and 0 when t is less than 0. This the graphical representation of step signal is for t less than 0, the magnitude of the signal is 0, and at t is equals to 0, the magnitude of the signal suddenly becomes a, and after t is equals to 0, the magnitude remains same. So this is a, and this a is known as step magnitude. So why we say step signal as sudden change? Because you can see here in this diagram that for t less than 0, the magnitude of the input signal is 0, but at t is equals to 0, suddenly the magnitude of the input signal shoots up to a, from 0 to a, and even after t is equals to 0, it means that for t is greater than 0, for all values of t is greater than 0, the magnitude remains same. The magnitude does not change. Unlike impulse signal, the magnitude of the signal does not become 0. It remains same. That's why we say that it is step signal is also known as sudden change. Now if the step magnitude a is equals to 1, then ut will become 1 for t greater than equals to 0, and 0 for t less than 0, and this ut is known as unit step signal, and it is graphically represented like this. Here this is 1, the step magnitude is 1. This is your unit step signal. Now this is step signal in time domain. In frequency domain, step signal is given by us, which is Laplace of ut, a by s, and for unit step signal, us is equals to 1 by s. This is Laplace of step signal. Now our third signal is ramp signal. So guys, ramp signal is given by rt. Rt is equals to at for t greater than or equals to 0, and 0 for t less than 0, and it is graphically represented like this. For t less than 0, magnitude of the input signal is 0, and for t greater than or equals to 0, the signal becomes this. So this is the graphical representation of ramp signal, and here A is equals to slope. Now when the slope of the signal becomes 1, or for A is equals to 1, what will RT become? RT will become T for t greater than equals to 0, and 0 for t less than 0. And this is shown like this. Here slope is equals to 1. Slope becomes 1, and this is known as your unit ramp signal. Now again, this is ramp signal in time domain. In S domain or in frequency domain, the ramp signal is given by Rs is equals to Laplace of Rt, which is A by S square. And for unit ramp signal, Laplace of unit ramp signal is simply 1 by S square. So this is Laplace of ramp signal. One more thing guys, that ramp signal is known as constant speed or constant velocity. So coming to our last test signal, which is parabolic signal, and which is also known as constant acceleration. So parabolic signal is given by xt is equals to at square by 2 for t is greater than or equals to 0, and 0 for t is less than 0, and it is graphically represented like this. 0 for t less than 0, the signal is 0, and for t equals to or greater than 0, the signal is like this. This is your at square by 2. This is your parabolic signal. And for a is equals to 1, this xt parabolic signal will become t square by 2 for t greater than equals to 0, and 0 for t less than 0, and this is known as unit parabolic signal. Unit parabolic signal. And this is also shown like this is the graphical representation of unit parabolic signal also. So this is your parabolic signal in time domain. In S domain or in frequency domain, or we can say that Laplace transform of parabolic signal is given like this. Xs is equals to Laplace transform of xt, which is a by s cube. And for unit parabolic signal, Xs is simply given by 1 by s cube. So these were your 4 standard test signals. Now we will see what are the relations between these standard test signals. So integration of delta t will give you step signal. It means that time integral of impulse signal will give you step signal. Similarly, integration of step signal will give you ramp signal, and integration of ramp signal will give you parabolic signal. So this is the relationship between standard test signal in the form of integration. Now we will see the relation in the form of differentiation. So here delta t can be given like this. Delta t is equals to d by dt of u of t. Derivation of step signal will give you impulse signal, and ut is equals to d by dt of r of t. Derivation of ramp signal will give you step signal, and last rt, r of t is equals to d by dt of x of t. Derivation of parabolic signal will give you ramp signal. So these are the relationship between standard test signal. Impulse signal can also be given like this: d2 by dt to rt, or d3 dt3 xt. So any signal can be related by these formulas. Any two signals can be related by these two formulas. Now one more thing is that you know that transfer function, which is function of s, transfer function is given by CS by Rs, that is Laplace of output by Laplace of input. Now if input is impulse signal, you know that Laplace of impulse signal is 1. So if we put Rs is equals to 1 in this formula, what we will get? Transfer function is equals to CS by 1. It implies that transfer function is equals to CS, that is Laplace of Ct. So finally we can say that if the input signal is impulse signal, then the transfer function is equals to Laplace of impulse response. This is a very important result. So if input signal is impulse signal, then the transfer function is Laplace of impulse response. So in numericals, examiner will give you impulse response, and if we take Laplace of that impulse response, then we will get transfer function. And once the transfer function is found out, then then output of the system can be found out with respect to any given input. For example, suppose that GT is impulse response. GT is impulse response of the system. Now you know that from this formula the transfer function is equals to Laplace of impulse response. So if we take Laplace transform of impulse response, then we will get transfer function. And once we get transfer function, then you know that transfer function is given by CS by Rs. So for any given input, once the transfer function is known, then for any given input, the output of the system can be found out. So that is the importance of this formula, and this is also known as weighting function. So guys, this was all about this video. If you have any problem related to this video, then please raise your queries in comment box. So thank you for watching the video. Signing off.